first of all, who comes to lateral flow world from ELISA world? I expect to see some, I heard a woo, I'll take a woo. Yeah, probably a lot of us come there from ELISA world, right? That's what we learn. Immunoassay-wise, that's probably the first thing you learn. But I think we've all come to realize probably as well, pioneering lateral flow assays, that sometimes those antibodies that work for ELISAs don't necessarily work for lateral flow. And why is that? We're going to talk about that today. So there is a little bit of math in here, but it's not scary math. It's math you may have learned in high school, you may have learned in college, and maybe you put by the wayside a little bit. But I'm here to sort of show you how we can bring everything together. The first thing I want to sort of just really emphasize is that energetics underpin everything. So in a lateral flow strip, you have the rate of release of the conjugate, the rate of the conjugate capturing the analyte, the rate of that entire thing flowing up the strip, the rate of the nitrocellulose membrane wetting, the rate that the test line captures the conjugate, the rate that the wick pad absorbs all of that liquid. So these are all identifiable and discrete processes. And the problem with the lateral flow as opposed to an ELISA is that, first of all, it's a directional flow. There's no mixing. There's no mixing at 37 degrees. There's no 1 hour for each step. There's no washing. And finally, at the end, there's no big enzyme coming in and making that wonderful signal that then you have to stop and read on a plate reader. For lateral flow, you've got sample going on. It's dirty. Maybe it needs filtration. You have directional flow. You've got release of the conjugate, and you've got one shot past that test line. And beyond that, if your sandwich is not made, I'm using a sandwich immunoassay for this, all your conjugate's going to end up in your wick pad. So a sandwich, you might be forming at least one part of the sandwich, so your conjugate might hit that analyte, but if that analyte is not then captured by the test line, that's it. Your particle ends up in the wick pad and your sensitivity is lost. So lateral flow, actually, it's kind of amazing that it works because there's so many things against us with lateral flow, and yet it does, because the antibodies in lateral flow are pretty amazing things. So because they are pretty amazing things, your lateral flow is really dependent on your biologicals and your processes that you use. And knowledge of these forces will enable you to take a look at your data in the lab and be like, oh, I see that. That means this, therefore I need to do this. Okay, so let's talk about thermodynamics versus kinetics. So thermodynamics are when we think of something and how much it's reacted, to what extent something has reacted. So in terms of, we think of a binding curve, a dose response curve. So your concentration's on the x-axis, whatever signal you have is on the y-axis, and you have a curve that looks like this. In kinetics, we have the same curve. And kinetics interrogates how fast something goes. So same situation, an antibody plus an antigen is in equilibrium with a product. Same thing with a kinetic situation, except for with kinetics, the x-axis is now time. These things are both related mathematically and conceptually. So if we think of something, how fast something reacts, that's probably going to be stronger, right? And in a way that is true, but there's a couple of different considerations here. So I'm going to start with thermodynamics, and maybe this is something that you remember from high school or college. Who remembers delta G? What does delta G stand for? I heard it. Gibbs free energy, that's right. What do we want? Like, do we want Gibbs free energy to be positive or negative? Negative, right. When we say it's negative, what kind of process is that? It starts with an S. Spontaneous. Yeah, so this is our reaction going to the right. So here's how we relate all of those things. So your thermodynamic association constant is the extent at which this product is formed. So this is products over reactants, and I'll tell you, my chemistry teacher in high school beat this into me really good because I still remember it now, and it's been a number of years. So products over reactants. So we have the concentration of the product here over the concentration of each of the separate reactants. So that's your association constant, which is also known as 1 over your dissociation constant. So the dissociation constant is just this going backwards. So delta G, Gibbs free energy, is dictated partially by this term, this association constant. So it's delta H minus T delta S, or negative RNT times the natural log of that association constant. If we get that association constant alone, we can see that this entire association constant, just as we said, is dictated by delta G. So if delta G is negative, Ka is greater than 1, and the products are favored, and that's what we want in lateral flow, right? We don't want this to go backwards, we want it to go forwards. If delta G is positive, Ka is less than 1. That's pretty much never going to happen when you have a good pair of antibodies. But if delta G is 0, Ka is 1, and that means that this situation is at equilibrium. So that's thermodynamics. Now we're going to bring in kinetics and see how the two are related. So same thing, same situation. The rate at which this proceeds is dictated by this on rate constant, and that's multiplied by the antibody, the reactants, concentration of the reactants. The reverse rate is the off rate constant times the concentration of the product. So when you take the ratio of these, it's just your products over reactants again, and there's your thermodynamic association constant. Conversely, your Kd is your off rate over your on rate. So these two terms relate thermodynamics and kinetics. Now here's the thing about Kd. We're used to talking about Kd because that is, you want a really low Kd, right? You want like a nanomolar, picomolar, femtomolar Kd. How good of a Kd are antibodies usually? Someone just yell it out. I know people know this. You're looking at like a micromolar, nanomolar, picomolar Kd. So we want antibody-antigen binding to be really, really tight. Biotin avidin that we also use in lateral flow sometimes, this is on the order of 10 to the minus 15th molar. So this is a femtomolar Kd. This is super, super, super strong. But the thing about Kd is we talk about it, but there's actually two terms in that Kd. There's the off rate over the on rate. So a smaller Kd, a better Kd, can be influenced by a higher association constant or a slower dissociation constant. So if something goes on really quickly, that's good. If something comes off really slowly, that's also good. But you can have trade-offs here. You can have a relatively slow on rate, but also a really, really slow off rate, and that's going to provide a good Kd. Now, is that good for lateral flow? Maybe not necessarily, because things happen fast in lateral flow. So this is something, and I promise I did not plan this, but Klaus is talking about SPR for the next talk. And I'm here to tell you, if you have SPR data for your antibodies, this can really, really help you. It's helped us at DCN before, if you have it. It's a really nice thing to have. So what we also have in lateral flow, I want to caution you, is it's not solution phase mixing. You kind of have a lot of things going on here. There's capillary forces pulling everything up as it's mixing. So there is a mixing going on, but it's a sort of a mixing with direction, mixing with flair. So Dan talked about parking area, and what he was talking about is the parking area of the carboxyl moiety onto a latex particle. What I challenge you to think about is the parking area of a particle on a nitrous cellulose membrane. So think of how big particles are. This helps me a lot because we draw cartoons a lot in the literature, and it looks like an antibody onto a gold particle, and we draw these the same size. But this is a picture that's to scale, and I want to show you that they're really not the same size. So this is a typical 40 nanometer gold particle. This is an IgG antibody, and these are to scale. So if you're using 100 nanometer latex, which is very small for latex in lateral flow, this is what kind of particle you're dealing with. If you use a 400 nanometer latex, this doesn't even make it onto the page because it's so big. So when we think about labeling our antibodies with something, and ELISA, you think of HRP or something like that, we're not sort of, it's kind of weird to think about when you use a particle, because you're not really labeling the particle or labeling the antibody with the particle. You're kind of labeling the particle with an antibody, right? So you've got this huge particle. Antibodies are only this size. It's like a lawn of antibodies on your particle. So it's pretty small, the antibody itself, but without the antibody, nothing goes, right? So we have to have this on here, onto these particles, and we have to keep it functional. So surfaces really affect this process. Adsorption can cause protein unfolding. Sometimes with ELISA, that's how we put everything down onto a plate, right? That's the first step. Sometimes you can lose up to 90% of your antibody activity just by doing that process. So it's just this lawn of protein that's not doing anything because your Fab region is destroyed. And the thing about that as well is, look at how little this guy is, and look how big this guy is. And latex doesn't weigh very much, it's not very dense, but it's big. So when you have this diffusing through solution, and then you have this going through the pores of your nitrocellulose, it's really going to slow it down. So what that's going to affect potentially, every antibody is different, and that's I hate saying that because it sounds like a cop-out, but it's true. Every system is different, and you have to treat every system as a bespoke system. If you have a good KD antibody because of a favorable off rate, you might find that your on rate is now affected by the presence of the fact that it's linked to a huge particle. So you might have to do some re-engineering there. The other thing is that, yeah, this big particle, look at this antibody. If you have an antibody printed on your nitrocellulose test line, if this comes and binds there, it's going to obscure the binding sites, potential binding sites on nitrocellulose for a whole other bunch of antibody binding sites. And so you might think that, why would you even use this particle? And I would say, yeah, that's a good question. Why do you use these big particles? We love these big particles, though. And the reason why is because they're so brightly colored. So for a latex particle, you can encapsulate a lot of organic dye in that 400 nanometer latex core. Definitely more than in a 100 nanometer latex. Gold is a different situation because it's not dyed. It's a plasmonic particle that actually has really good optical absorption just at 40 nanometers. So we still use we think of lateral flow as those two red lines, right? So that's typically particles. So everyone uses particles. Most people use particles. There might be some obstacles that you need to overcome. So if you have that antibody with a low on rate, you could go to a smaller particle. What you can also do is just label that little antibody with a small molecule, maybe a fluorescent dye, instead of a really big particle. We've had that work before with antibodies that have had low on rates. Increased particle size works as well. Definitely had good luck moving from, say, a 200 nanometer latex to a 300 or a 400 nanometer latex. If you have a particle that is offered in a number of different sizes, that helps. Eventually, if you do it too much, it will become too big to flow through the nitrocellulose membrane or be released from the conjugate pad. So you are sort of limited here. Here's the thing about lateral flow too that always gets me, is that when you're looking at that test line, or your reader is looking at that test line, you're seeing the top 10 microns. That's it. 90% of that signal you're not detecting. So unless you're doing it with some sort of magnetic detector, you're not seeing the entire signal. So again, it's amazing that any of this works. Loading more antibodies is it seems kind of obvious, right? But it really does work. If you load it too high, you're at risk of making your nonspecific binding come up, but it can really, really save your assay. Just give you that little bit of extra sensitivity you need. So a lot of these things matter with lateral flow. And I don't want it to be too much of a cop-out, but you have to try everything, even if it's something weird. Different sizes of particle, different loadings of antibody, and you might need to push it up or down. You could switch to a biotin-avidin system where you have an in-solution biotinylated antibody and an avidin at your test line. That's definitely something that would help your sensitivity. But it really depends on your pair of antibodies. Switch your antibodies around. Try a different pair. These are things that we do routinely at DCN all the time for assay development. And I guess the last thing I want to leave you with is I had a lot of fun making this chart, and I think it put a lot of things in perspective for me. So this is a log scale size chart going from 1 nanometer all the way up to 1 millimeter, showing some of the more crucial areas of lateral flow. So you can see like that the smallest dimensions, we have things like biotin and small dyes. And in the larger dimensions, we have things like material overlaps and lateral flow. And then in between here, you've got your particles, your labels. Then here comes your conjugate pad, your nitrocellulose. And this is how thick your membrane is. So these things, you can see why when you get a little too big in your particle, now it's not going to flow through your glass fiber conjugate pad and be released. So I always try and keep these sorts of things in mind when I'm developing is how big are things? I know that sounds very silly, but it really helps when you think of the relative sizes of things of, oh, that won't work because this is too big to fit in here. Or if you think of, if you have a tiny antigen, are there really 2 epitopes on your, or really tiny, yeah, tiny antigen. Are there 2 epitopes on that antigen to which you can hook 2 antibodies? Really think about it. So I did write a white paper on this, and this is available on the DCN Dx website. I also have a poster in the back, so please come talk to me at the poster session, and I'd be happy to take any questions you have. Thank you.